So we're talking about continuity today. We've talked about it already a little bit, and I've been telling you that this day is coming, and here it is. And continuity is a simple idea graphically, like we've already talked about that, and your intuition as to whether a function is continuous at a point is fairly accurate, I think, like it's kind of obvious, right? But we are going to formalize it, talk about when functions might not be continuous, and our last example is a formal sort of proof about whether a function is continuous at any particular point, or what we're actually going to do is at all points, and state whether it is or whether it isn't, and that kind of thing, okay? So even though it's a simple concept overall, I think, we're going to formalize it, which makes it, trickier because you have to do it the right way and you have to kind of understand more of the small details. Does anybody remember, we sort of talked about this, like in your own words, what makes a function continuous at a particular point, or how is continuity of a function related to limits? If we think about the examples of limits from sort of the second day of the course. Yisha? Close. That if the left-hand limit equals the right-hand limit, then the limit exists. Ibrahim?
The limit and the y value of the function are the same value.
Good. Okay, so I'm going to say it this way. So that was if the limit is equal to the y value of the function at that x value, or instead of y value, I'm going to call it the function value. But okay, whoa, what's going on here? If the value of the function, this is the sort of natural language way of saying it, right? We already wrote down the definition before. We're going to do it again in a minute. If the value of the function, which is f at x, or let's say f at a, at a point, so a, is equal to the limit at that point a, so when x equals a, then the function is continuous at that point. And a little bit of review. Is that okay? You got that? So a little bit of review. This could look like this. This function is obviously not continuous at that point, let's say. In this case, the point would be a, x value of -3 or whatever it is. Okay, so not continuous. Why? The limit doesn't exist at that point. If the limit doesn't exist, the limit can't equal the function value. This is an example where the function exists, but the limit doesn't. Okay, what about this? Continuous at that point? No, because now the limit exists, but the function doesn't. If I had a pop-out where it was like this, then the function would also exist and the limit would exist, but they don't equal each other, so still not continuous. I mean, by continuous, we literally mean it continues through that point and exists at that point, right? And continues sort of flowing naturally through it. Okay, and then here's another example. If we're talking about that point, the limit exists, the function exists, they're equal to each other, so the orange one there would be continuous at that point. And it's a parabola, so I would imagine it's continuous at all other points. Sometimes we're asking about the function as a whole. Sometimes we might just be asking about one particular point. Okay? That depends on the question, and that has to do with just, what kind of a question is, what their teacher asks, what they're looking for, kind of thing, right? Okay? There are 3 types of discontinuities. What do you think they might be? When could a function be discontinuous? At a pop-out. So one of them, we'll call it a pop-out, or we call it a break, or a jump. Okay, something like that. Sorry? Nice. Oops. And the third? A hole. You got it. Okay, so a pop-out and a hole are similar, just a pop-out, the function exists somewhere else. It still kind of looks like a hole, they're similar. Okay. Okay, let's look at breaks. A break will probably have will probably be a piecewise function. Okay, so it might be something like this. Let's see. This is an easy one. 2 when x is less than 5, and negative 2 when x is greater than or equal to 5. So if this is 5, that's what that would look like. So that's a jump. It's jumping. The function is jumping from one location to another. You call it a jump or a break. Okay, and a pop out. Would look something like that. Its equation would also be piecewise. You'd probably see it in 3 parts. The part below the pop out, and then the part after the pop out. I'm not going to write down that equation. Okay, 2. What was 2? Vertical asymptote. Well, we know what that looks like. What would be the equation of a function with a vertical asymptote? Something like this. Now, if I made that x cubed minus 27, it would have a hole. So this looks like it has a vertical asymptote at x equals 3. And it's going to look like that, or like that. Okay, something like that. Vertical asymptote. Not continuous at that point. Simple so far, I think, right? And the last one was a hole. So it looks like a vertical asymptote, and some people in MHF have a hard time with that, right? But this would actually look like, be something like this. And then at 3, it would have no roots. We have a hole. Simple enough, right? Here's another cool one. This is for a pop-out. Or sorry, it's not a pop-out. It's a jump. This one's neat because it's not a piecewise function. Okay, its equation for this one would be, and you could play around with this, graphing it with technology would be kind of interesting. So this has a vertical asymptote, and I think it goes like this, and then it goes like this at, this is 2 and this is 3. So it has a jump in it, which is interesting. Looks like it would have 2 vertical asymptotes, but one of them is actually a jump because of the top. Absolute value isn't something that we're going to explore very much, but they can make some interesting graphs. Is that good? No questions about that? So, straightforward. Kind of MHF stuff, thinking like, what do we know about functions algebraically? What do we know about them graphically? What would they look like? That sort of thing. Part of today is you have to be able to look at a function, understand the type of function it is, and sort of figure out where might it be discontinuous. And then that might be something you have to explore. Okay. The formal definition of continuity, is this. We wrote this down before. We're going to do it again. A function is continuous at x equals a if and only if the limit as x approaches a of f at x exists and the function exists, and the limit as x approaches a of f at x equals f at a. This is the sort of formal way of saying what we said in the opening, right? Yeah? Sure. Good? Okay, now 3 cases for discontinuity. As they relate to limits. This is not the same as the 3 cases that we talked about before. Okay, not the same thing. Case number 1. F at x does not exist at x equals a. If f at x doesn't exist, it can't be equal to the limit. Right? What would cause f at x to not exist at some point? What kinds of properties of functions would cause that? Very good. So a hole or vertical asymptote. Again, you could sketch these quickly. The limit might exist, but the function doesn't. Case number 2, the limit doesn't exist. What would cause the limit to not exist? Yeah. So if the left-hand limit does not equal the right-hand limit, what would cause that? A jump, a break, or a jump? What else? Repetition is fine. Vertical asymptote as well. Right? I should be marking this. This is A. This would be x equals A. This is A at that point. I mean, these are made up sketches, but like you look at it and you see, well, it looks like they're continuous everywhere else, but A is what we're asking about right now, not continuous at A. What would be the third case where we would have discontinuity? Ibrahim?
The limit doesn't equal the f at x.
Yeah, so f at A does exist. The limit as x approaches A of f at x does exist. But they're not equal to each other. What's one example of this? Anybody think of one? A break or a jump. If it's a jump like this, the limit doesn't exist. Yeah. I know what you're thinking. And what do we call that? It's got a different kind of a name. A pop-out, right? That's what you're thinking, where it's like, so that's what you meant, like this? But in this case, the function doesn't exist unless I add a pop-out. Okay? Any questions? I think I have a blank page in here in case I need more space for my diagrams, but I squeezed them all in. All right, so now let's start doing some examples. I think that the first little bit of this lesson always seems obvious to people, and it's like, man, we spent a lot of time talking about something that's fairly simple. And I mean, you're kind of right, but there's a continuity of functions is kind of a big deal. We spend one day on it, and you're going to see when we start doing examples that there is actually lots of opportunity for errors or for misunderstandings when we start actually doing the process. So formalizing it and thinking about the three cases for discontinuity, that kind of thing, helps if you think about it explicitly. Case 1, case 2, case 3, that sort of thing. Find the value or values of x at which the function f at x is discontinuous and state the type of discontinuity. This is one of the types of questions that you're going to see in the practice and on quizzes and tests, that kind of thing. Looking at this with our understanding of functions, what type of function is it? Has a name, Ibrahim? It's a rational function. Where would you suspect we might, or maybe you already know, have discontinuity? And where?
X equals 4.
At 4, when x equals 4, because that's what's going to give us a 0 on the bottom. Very good. And you would suspect that it's a vertical asymptote, but actually we don't know that yet, do we? What else could it be? It could be a hole. So what would you have to do for this question? Factor the top and the bottom. This is a tricky thing that comes up a little bit in MHF, but I think you'll find it comes up more in calculus. When you get 4 minus x, what is that? It's hiding something. And it becomes x minus 4. And then you could 4 plus x or x plus 4, doesn't matter, right? Yep.
If you factor it from the beginning, is that fine?
Yeah, of course, yeah. Factor out the negative first. Yeah. You could do it all in one step. I mean, that's not, yeah. So it turns out it has a hole, right? But this is something that you have to start spotting, knowing that 4 minus x can be turned into x minus 4, right? But you have to factor out the negative. So therefore, f at x is discontinuous at x equals 4 because of a hole. If you factored it and there was no hole, then you'd have a vertical asymptote and you'd be done. You would just say vertical asymptote instead. Okay, make sure you state why. Good? We have another one here. There we go. What should we do this time? That should be 15x, by the way. What do you think we should do? Factor, very good. Oh, and that should be 10. Ooh, I gotta go try to fix this one. Yep.
It's discontinuous at x equals 5.
Mm-hmm. Why?
Because the vertical asymptote.
Nope.
No, you cancel out the x minus 5.
Mm-hmm. So what does that make it when you have it on top and bottom? It's a hole. So therefore, f at x is discontinuous at x equals 5 because of a hole. And because, so what do we call that? Got it. And f at x is discontinuous at x equals 0 because of a vertical asymptote. Everybody okay? It's quiet. Is this too easy or is this strange or what? Like, what do you think? Not interesting? What? What is it?
It's sort of fast.
It's going fast? Okay, fair enough. One more example of these, and then one more different example. I sort of mentioned it for the first example, but for the second example as well. We looked at the two places where it was discontinuous, the hole in the vertical asymptote. Would there have been another place that it might be discontinuous? This is where our work in MHF is so important. Like all of those graphs that you sketched, or that you were supposed to sketch but you didn't because you didn't do your homework. All of those rational functions, did any of them have other places where they didn't exist or where something funky was going on, or was it just a smooth curve? What do you think? Anya, did you answer that? Not sure? Because you got to know something about these functions to know where you have to check. We didn't check anywhere else. We didn't do any checking for those two rational functions to see if they were discontinuous in other places. We know they're going to be a smooth curve. Rational function will have maybe a hole, some vertical asymptotes. Horizontal asymptote doesn't have to do with continuity because the function exists, right? It's not y values that we're looking at, it's x values. So it's just vertical asymptotes and holes for rational functions that we would have to look for. There's not another place where that would happen, right? But you have to know that with confidence. What if it was a trig function? What if it was sine x? Yeah, continuous everywhere, right? They don't have holes. Did you ever graph a trig function with a hole or a vertical asymptote? Besides, I mean, tan and secant, they do, but no. So you don't have to. What about this one?
You're going to figure out what x equals at 1?
Why at 1 are we curious? But would you check anywhere else? Dawson? No? Why? Why wouldn't we check at -5 or at 10?
It's less than 1.
Yeah.
So it gives us the function that it equals.
And which is what kind of a function? So if we're talking about this one, degree 2, quadratic, and it just exists everywhere for every, like what's its domain, in other words? It exists everywhere. What about the other half of this graph? Again, its domain is x is an element of the real numbers. It exists for all values of x. So above 1, we know that it's just smooth. Below 1, we know that it's just smooth. I'm curious about what's happening at 1. There could be lots of things happening. Let's check. So how do we do this? We've actually seen this before. We do a left-hand limit and a right-hand limit. So we do the limit as x approaches 1 from the left of f at x, which is the limit as x approaches 1 from the left. And if I'm approaching from the left, I'm the quadratic. And I can just sub in and solve. And the right-hand limit, if I'm approaching from the right, I'm the other function, the linear function. So, what does this tell us? It's discontinuous when x equals 1. And the limit doesn't exist. Very good. So the left-hand limit does not equal the right-hand limit. Does the function exist at that point? Yes, the function exists, but the limit doesn't exist. Okay? Therefore, discontinuous at x equals 1 because of a break or a jump. Color that one in. Something like that. Okay. So that's one type of question that we're looking at today. Checking for discontinuity and stating the type. 3 cases for discontinuity. The limit doesn't exist, like that. The function doesn't exist, like the holes that we saw in the vertical asymptotes. Or they both exist, but they're not equal to each other, which would be a pop-out, which would look like a piecewise function, right? Yeah.
Isn't the quadratic the one including the point? Not the
Oh, you're right. Whoops. Thank you. And then the sort of reasons are breaks, vertical asymptotes, holes. Any questions before we move on to the next example, which is a big one?
In our answer, how much do we have to specify?
Your answers for these should look like that. You got to show some work. You can't just look at it, do it mentally. You got to show it, and then you got to make this statement, right?
Yeah.
It's discontinuous at whatever value because of break, vertical asymptote, hole. Does that mean? Yep. This is the one where showing your work is trickier, and people miss all kinds of details. This one's almost like a proof. We take this one like a proof. Next unit, we're going to be doing a whole bunch of formal proofs. So get used to the idea of these things. We did a couple of formal derivations or proofs in MHF, and so you already know that you have to write them a very specific way. You can't leave steps out. So part of learning proofs is learning what's important to show, what you have to show. This one's not, like, it is kind of a proof, but it's not a derivation proof, so it's a bit different. So people, I think, misunderstand what's important to show. So you really want to pay attention to that and understand the bigger concept of what we're doing for a question like this. So these ones are like a formal discussion of the continuity of the function. Not just where is it discontinuous, the continuity of the entire function. So we have to look at the entire domain of the real numbers. And your proof or your solution, your write-up, has to touch on every real number. Okay? What does that mean? Well, where might something interesting to this function be happening? There might be something going on, some kind of break or hole or jump or whatever at 2. Like we talked about before, what about less than 2? Anything going on? Nothing, right? It's just a polynomial. And they exist, their domain is x is the element of the real numbers. What about greater than 2? No. But it's not enough to think that. We have to say that when it's a discussion of the continuity. Okay? So we do this. For x less than 2, f at x is continuous because it is a polynomial. For x greater than 2, not greater than or equal to, just greater than 2. F at x is continuous because it is a polynomial. This might seem repetitive if a lot of the questions have this and you just want to skip it. But when this question comes up on the test, you have to make those statements. You have to touch on all the real numbers. And we've touched on almost all of them, haven't we? We've touched on every single real number except for one. The one that we're suspicious of. So we've covered the vast majority of our bases in terms of the continuity of this function, right? I'm going to check f at 2 and see what it's equal to. F at 2 equals 2 minus 2. So f at 2 exists. You're going to need to calculate that anyway, so it makes sense to calculate it now and show that it exists. Okay? Because one of the reasons for discontinuity is the function doesn't exist at that point. So we've eliminated that. Now what do we have to do? Anybody know? Ibrahim?
Find the limit then.
And what's that going to show us?
If it's equal to the function value,
Then?
then there's a limit there.
Then what?
Then it's continuous.
Right, then it's going to be continuous at 2 as well. Very good. So we got to check that it exists. We got to find its value. Then we're going to find the limit at 2. And if it's not equal to the function value, then it's discontinuous. Some kind of a break. If it is equal to, then it's continuous. Okay, so left-hand limit. Limit as x approaches 2 from the left of f at x is the limit as x approaches 2 from the left of x squared minus 4. Now I can just sub in. So far so good. Everybody okay? Aha. Left-hand limit equals right-hand limit. Therefore, the limit as x approaches 2 of f at x equals 0, right? So just like Ibrahim told us, if the limit is equal to the function value, that's what we opened with saying is like the definition of continuity. If the limit exists and the function exists and they're equal to each other, then it's continuous at that point. Remember, we already talked about all the other points on the graph because it's just a polynomial everywhere else. So the limit, there's a lot of writing in this and people don't want to do it. But this is a formal process, so you have to. All of these little statements that I'm making are all 100% required for the formal discussion of the continuity of a function. Okay, so the limit as x approaches 2 of f at x equals 0, which equals f at 2. Therefore, f at x is continuous at x equals 2. We already talked about how it's continuous everywhere else. So in this case, one more final statement to summarize everything. Therefore, f at x is continuous. For x, element of the real numbers. For all x. For all real numbers. If it wasn't continuous, then you would just say left-hand limit does not equal the right-hand limit, or limit does not equal the function value, therefore discontinuous at x equals 2. Yeah. Right? And you'd be done. But because it was continuous, you have to summarize into one final statement. If you left this out, that's loss of marks. Okay? You can't leave it to your reader to put the pieces together, to realize that you said everything below 2, everything above 2, and 2, which just means everything. It's your job to summarize and put those pieces together. I can't remember, but 5 or 6, something like that. Like it's fairly big.
If, say there was a vertical asymptote or a hole, so there wasn't a value for the function, would you go XER such that x doesn't equal blank? Like the x value for that hole?
No, I think you would just leave it as it's continuous below 2, continuous above 2, discontinuous at 2. I'm gonna go back over this one more time. We started by recognizing this was a piecewise function. I took care of the easy parts first. Below 2, it's continuous everywhere because it's a polynomial. See what you have to know about the nature of functions to know that. It's an easy one. I hope that everybody in here knows that polynomials exist on the entire domain of x, right? All real numbers. But you got to know that about other functions too. What if it's a trig function, or what if it's something else, right? So you got to know that about like all the different functions we've talked about. What about absolute value? All the different things. Okay. So less than 2, it's continuous everywhere. I'm done with all that. I can leave it. Greater than 2, continuous everywhere. Done. Then we checked to make sure it exists at 2. I mean, I kind of know when it says greater than or equal to 2. Like I know it's going to exist at 2, but I'm showing it by finding its value, stating that it exists. Then we have to check if it didn't exist somehow. And you wouldn't be done. You might still have other stuff to do, but then you would know it's not continuous there. Like you'd be done. You wouldn't have to check the limit. If the function doesn't exist there, it's not continuous. Okay, that doesn't usually happen. So then we have to check the limit. So I did left-hand limit, right-hand limit. They're equal to each other. I made that statement, made the statement that the limit is equal to 0. Okay, then I took that and pointed out that that's also equal to the function value. This is what I'm saying. All these little statements are required. Okay, you leave one of them out, then it's not a full formal process. So I said they're equal to each other, which is the definition of continuity. Therefore, it's continuous at x equals 2. And because I can summarize it, instead of in 3 statements, I can say it in one statement. I have to re-summarize f at x is continuous for all real numbers.
If it wasn't continuous at 2, like if the L if they didn't equal, would you just write discontinuous because of?
If the left-hand limit and the right-hand limit didn't equal each other, then you would say discontinuous at x equals 2. The limit doesn't exist. If it just wasn't equal to that, then you would say discontinuous at x equals 2. Because of a break, I would imagine, right? Yeah. Other questions?